Hello everyone, welcome back to our channel. Today we're diving into the fascinating world of microprocessor, specifically focusing on the direct memory access or DMA operation in the 8085 microprocessor. If you're new here, don't forget to hit the subscribe button and click the bell icon to stay updated with our latest videos. Before we get into the nitty-gritty of the DMA, let's understand why it's important. In a typical microprocessor operation, the CPU is responsible for transferring data between memory and peripherals. This can be quite inefficient, especially for large data transfers, as the CPU gets engaged down with these tasks, reducing its ability to perform other operations. This is where DMA comes in. Direct memory access allows certain hardware subsystems to access the main memory system independently of the CPU. This is particularly useful for high-speed data transfer operations such as reading from or writing to a disk or streaming audio and video data. In the 8085, DMA operations are managed using two key signals, hold and HLDA. Let's break down how this process works. At first, when a peripheral device needs to transfer data to or from memory, it sends a DMA request to the DMA controller. This is done using the hold signal. The hold signal is sent to the CPU, indicating that the peripheral device needs to use the system buses. After that, the 8085 microprocessor completes its current instruction and then acknowledges the hold request by sending a HLDA, hold acknowledge signal, back to the DMA controller. This indicates that the CPU has provided the control of the system buses. In the third step, once the HLDA signal is received, the DMA controller takes control of the system buses. Then the CPU is now in a hold state and does not interfere with the data transfer. This allows the DMA controller to directly manage the data transfer between the peripheral device and the memory. After that, the DMA controller manages the data transfer directly between the peripherals and the memory. The process continues until the data transfer is complete. The DMA controller uses the address bus to specify the memory location and data bus to transfer the data. Then after the data transfer is complete, the DMA controller releases the hold signal, allowing the CPU to regain control of the system buses and resume its operations. The CPU can then continue executing its instruction without having been significantly delayed by the data transfer. The main advantage of using DMA is that it frees up the CPU to perform other tasks while the data transfer is taking place, significantly improving the overall efficiency of the system. This is especially important in real-time applications where timely data processing is crucial. In the 8085 microprocessor, DMA is particularly useful for applications that require fast and efficient data transfer, such as audio and video processing, data acquisition systems, and communication systems. To summarize, the DMA operation in 8085 involves the following key steps. Peripheral device sends a hold signal to the CPU. CPU acknowledges with a HLDA signal. The DMA controller takes control of the system buses. Data transfer occurs directly between the peripherals and memory. DMA controller releases the hold signal and CPU resumes control. And that's a wrap on our detailed video of DMA operation in 8085 microprocessor. If you found this video helpful, please give it a thumbs up and share it with your friends. Don't forget to leave your questions and comment below. Thanks for watching and we'll see you in the next video.